Okay guys, let's have a look at steel today. Steel was one of the topics I've dealt with in my bachelor's thesis. So in this video I want to show you how steel is produced, where and why greenhouse gases are produced, and also what measures do we have to reduce them in order to decarbonize the steel production. As always, starting off with a short motivation. Steel and iron is nearly everywhere. We have it mostly in the building and infrastructure, but also mechanical equipment, automotive, metal products, electrical equipment, and so on. This high demand of steel has as consequence that steel is the most produced metal in the world. We can see here that iron ore is by far the largest mined metal in comparison to all the other metals. Together with the rather carbon-intensive production of nearly 2 tons of CO2 equivalents per ton steel, the iron and steel sector, as a consequence, has a significant share on the global greenhouse gas emissions. And by significant, I mean that iron and steel sector is responsible for around 7% of the global total greenhouse gas emissions. To better understand these emissions and how they are created, we now look closer into the production of steel, shown here in the flowchart. At first, there are 2 preparation steps, the sintering and coking. We will start with sintering now. So if you Google sintering, you might come across some figures like this. At first glance, you could think that this looks very complicated, so I have simplified it in my notes, where we now switch to. Here you can see the simplified version of the sintering process. The goal of the sintering process is to prepare the iron ore for the application in the blast furnace. This is done by mixing the iron ore with mainly coke or sometimes also other materials and pour it onto a treadmill. You can see here the treadmill moves to the right. We now have the mixture of coal and iron ore, which is then put onto a burner. This burner ignites the coal, and the coal is now burning through the bed to the bottom. But because the treadmill is moving to the right, you can see that this burning to the bottom of the mixture bed happens into a more diagonal line here. The reason for that is that if we burn the coal and iron mixture, these iron ore can clump together, can fuse together to get from a form like this to a form like this, which is better suited for the blast furnace application. Another advantage is that the iron ore is already partly reduced. Iron ore is typically found in iron oxides, so iron and oxygen, and we only want this or iron, so we have to get rid of the oxygen. This is done by a chemical reaction with carbon, where iron and also CO2 is formed. So we have the burning of coal, which releases CO2, but also the chemical reaction, the so-called reduction of iron ore, which also releases CO2. And in the end, we have the sintered iron ore, which can now be used for the blast furnace. Going back to the figure I've shown you before, you can now understand the mixture area, the combustion area, and also the sinter area. I've shown you that the raw material for iron and steel production are mostly iron oxides, and that the sintering process is used for the preparation of properties for the blast furnace operation of the iron ore. CO2 is mainly created by burning of coal in the mixture bed and also partly of the reduction reaction, which also releases CO2. In the end, 22.4% of the total production emissions are related to the sintering process. The second preparation process was coking, and during coking we addressed the coal production. Coal does not always have the desired properties for blast furnace operation. Because of that, a coking process is used to achieve the desired properties. I will explain the coking process in my notes again. We have coal and we heat it up to high temperatures, but this heating is done in the absence of air. The heating of the coal in the absence of air brings the so-called volatile components in the coal to gas out. So we have water vapor that escapes, but also other chemicals like oils or gases that escape the coal. And in the end, we have coal with a higher carbon content, which also translates to a higher calorific value. You can see here the so-called batteries where this is done in. To summarize it, we heat coal in the absence of air, with the goal to prepare the coal into coke for properties in the blast furnace operation. To achieve these high temperatures, fossil fuels are typically used, and in the end 24.6% of the total production emissions are related to coking. So now that we have spoken about the preparation for the blast furnace, we can now have a look at the blast furnace itself. Again, researching the blast furnace in the internet or in school books, you will find figures shown like here. These figures go more into detail than we needed for our video, so I will show you now the simplified version again. We've talked about the sintering process, preparing the iron ore, and also the coking, preparing the coal. The sintered iron ore is now given into the blast furnace together with the coke. Inside the blast furnace, the coal is burned, releasing high temperatures, rising from the top to the bottom. The process we are interested in this video is very simplified, the reduction process. Like during the sintering process, we have iron oxides and we have carbon from the coke. We want this iron here, so what we do is that this oxygen reacts together with this carbon to form CO2. This leads for the iron to be freed, and so we have pure molten iron because of the high temperatures at the bottom. So with this reaction we form CO2, which gases out into the atmosphere here, and we also have molten iron that is collected at the bottom, which moves to the bottom, and there we can get this molten iron out of the blast furnace. This molten iron at the bottom is not 100% pure because some of the carbon is solved in it. This will be relevant for the next step. So getting back, we understand that the sintered iron ore is put together with coke into the blast furnace, where the coke burns and also the reduction reaction happens to form the molten pure iron and also CO2. Summarized, we have sintered iron ore and coke as input. We have increasing temperatures in the blast furnace, melting the iron, and the CO2 is produced by the burning of coal or coke and also the reduction reaction. In total, 42.2% of the total production emissions are related to the blast furnace. I have foreshadowed that the carbon that is solved into the raw iron, into the molten iron here, is significant for the next step, and the next step for the steel production is the blast oxygen furnace. So raw iron has a carbon content of around 5%, and to achieve steel we have to lower this carbon content to below around 2%. This is done by blowing pure oxygen into the molten iron. Again, if we look at my notes, we have now the molten iron with the carbon content, and we put it into the converter next. In the converter we have the molten liquid iron with the carbon content, and we now blow the pure oxygen into it. So oxygen now reacts with the carbon in the liquid iron, which forms CO2, and now the carbon gases out. With this process the carbon content in the liquid iron is lowered and we achieve steel, but we can also see that the reaction with oxygen leads to further CO2. Again, the injection of pure oxygen in raw iron leads to the production of steel by lowering the carbon content, but CO2 forms by the reaction. In the end, this is not that significant with 1.2% of the total production emissions. Now we get to the last step. We now have the raw steel, and steel is now finished. So we want the steel in different forms or different alloys and so on, and this is done during finishing. Here's a flowchart of steel production. So we can see here we have covered this part with iron ore, sintering, coke, blast furnace and blast oxygen furnace, but now the molten steel is casted and can be put into different forms, different alloys and so on. So finishing is the secondary metallurgy and the alloying, the manufacturing of the steel, where the electricity for the machinery is responsible for most of the carbon emissions during finishing, which make up around 9.6% of the total production emissions of steel. We now have the distribution and also the explanation of greenhouse gases in the steel production, shown here and here. And with that knowledge, we can have a look on reduction measures. Starting with finishing, I've said that electricity has a major part in finishing emissions, so renewable electricity would be a solution. The majority of emissions comes from the blast furnace, so we have to reduce the blast furnace emissions. And to address sintering and coking, there are measures with the goal to avoid coke and coal use. Both of these ideas, which address the majority of the steel production emissions, can be split into two categories. We have the adaptation of the conventional production route by using biomass, CCUS or hydrogen, but we could also use alternative production routes by, for example, recycling or the direct reduced iron path. Now go more into detail on these reduction measures. Biomass proposes the use of charcoal instead of fossil coal. This basically says, okay, let's burn wood instead of fossil coal. The advantage is that the carbon dioxide that is emitted was previously sucked out of the atmosphere when the tree was growing. So we have so-called biogenic emissions here, and the idea is that by burning wood there's no extra CO2 emitted into the atmosphere, which would be the case if we would burn fossil coal from the ground. The problem with biomass is that we would need a tremendous amount of wood. And while this could be useful to reduce emissions for some single plants where the conditions are right, for the large-scale application for the whole industry it would not be feasible because of the high amounts of wood that would be necessary. Also in regard of the already ongoing deforestation and loss of biodiversity. Next up is carbon capture, utilization and storage, short CCUS. The idea behind that is that we collect the waste gases from the blast furnace, so for example we capture the CO2 before entering the atmosphere, and we can either use the CO2 in other industries, for example for e-fuels or in the chemical industry, or we can store it to prevent it from leaking into the atmosphere. The challenge with CCUS is that it can't capture 100% of the CO2 from the blast furnace. It would need a high energy demand, so high electricity, to separate the CO2 from the waste gases, and also there is at this moment insufficient infrastructure to transport the CO2 and also to store the CO2. Moreover, carbon capture does not address the core root of the problem, so it does not address the creation of greenhouse gases, which leads to my opinion CCUS as a bridge technology for existing blast furnaces, but it should not be seen as a way to build more blast furnaces and just equip them with CCUS. The next topic is hydrogen. By using hydrogen as a reduction agent instead of coal, we could form water instead of CO2. So we have seen that in order to get iron, we have to separate the iron from the oxygen, and we do that by using coal, which with a reaction with carbon and oxygen releases CO2. If we now use hydrogen instead of carbon, the reaction of oxygen and hydrogen leads to water, which avoids carbon dioxide emissions. However, for the blast furnace operation, this would mean expensive adaptation of the technology of the blast furnace, and also it is unclear how the high amounts of hydrogen would be supplied now. And combined with the rather low greenhouse gas reduction potential in the blast furnace operation, hydrogen used to adapt the conventional production route is not that promising. So, as we can see from this, all of these have some disadvantages. So we have to look at the alternative production routes, where we have the recycling with the so-called electric arc furnace, where we can just recycle scrap by using a furnace operating with electricity instead of fossil fuels. Here the electricity supply is crucial. The electric arc furnace recycling already starts with a lower energy consumption, but what electricity do we use for the operation decides the overall environmental performance. So if we use renewables, this environmental performance is better if we use electricity from fossil fuels. In addition to that, we cannot count on recycling to meet all of our steel demand. We require more steel than we produce scrap. Only around 40% of the steel production in the future could be met by recycling. So Even with the higher rates of recycling, we still have to look at the primary production or the new production of steel. And here the most promising production way is the direct reduced iron EAF route. Instead of a blast furnace, we have direct reduced iron, which operates with a lower energy consumption and also electricity instead of coal. We still need a reduction agent where we can use natural gas at first and can transition to hydrogen. On the one hand, we have a high reduction potential of greenhouse gas emissions, which also offers a future-proof design by using the now currently available natural gas as a reduction agent, but also the possibility to transition to hydrogen with low expenses and low technical challenges. But on the other hand, there are still emissions due to the electricity consumption of the direct reduced iron of the EAF, which is needed after we produce our iron from the direct reduced iron, and the production of hydrogen, or that the iron ore still have to be prepared, which adds to the emissions. This knowledge enables us now to derive feasible reduction measures for the production of steel. Starting off with the increase of recycling and a transition from the blast furnaces to the direct reduced iron in the primary production. Hydrogen should not be used for the blast furnace or to adapt the blast furnaces, as I've shown you that it is more efficient using in the direct reduced iron. And in the end, carbon capture is a useful technology to reduce the emissions of the existing blast furnaces. So they should be used during the phase out of existing blast furnaces to bridge to the new primary production via direct reduced iron here. But keep in mind that all of these are in the end dependent on renewable electricity. So we have the recycling in the electric arc furnaces, we have electricity needed in the direct reduced iron EAF pathway, hydrogen needs green electricity for a good environmental performance, and so does the carbon capture plant. And that's it for this video. Of course, there are other measures beside the measures I've presented you in this video. And if you want to go more into detail, I can leave you the link to my bachelor thesis down below. As always, I hope you learned something from that today and it was kind of interesting. You now understand the production of steel, you now understand where and why greenhouse gases are created in the steel production, and you also have a broad overview on measures that would be implemented or that can be implemented into the steel production. See you in the next video and für die Umwelt.